Hello everyone, Aaron here and welcome back to Leetcode. Today we're doing the contains duplicate 2 problem. Given an integer array nums and an integer k, return true if there are two distinct indices I and j in the array such that nums I is equal to nums j and the difference between I and j is less than or equal to k. So, if we're given 1, 2, 3, 1, and k equals 3, we can see the ones match, and they are 1, 2, 3 apart from one another, and that's okay. Here we see there are two ones that are the same, but they're too far apart, they're 2 apart. But there's also two ones here that are just 1 apart, and that's fine for k. Here we have k equals 2, so these 1s are 3 apart, these 2s are 3 apart, and these 3s are 3 apart. So although there is lots of duplicates, there are no duplicates that are close enough to one another. Now, with this kind of problem, it's really easy to dive in and think, I know, I will just do a for loop and I'll say, right, I'm looking for a 1, I'm going to go along and find the next 1, and if it's too far away, then I'm going to stop. But the complexity of this algorithm is very high, basically. We have to scan through every item, 1, 2, 3, 4, 5, 6, so on and so forth. That is an order n operation, but for each one of those, I then need to scan again and see if there is something within distance k, and that could take up to order n as well. So this is an order n squared algorithm. Now, depending on your field, that's maybe not terrible. So my area of expertise is AI, and quite frankly, if something is polynomial at all, it's probably a good day. Normally we're dealing with something that's exponential if it's computable at all. But if you're actually trying to implement something that will work more widely, you don't really want n squared. N squared is kind of slow. In particular, we can see this could be a very, very long list, 10 to the 5. So we don't want to be doing this n squared algorithm. Now, I suspect the n squared algorithm will work just because this is an easy problem. But it's bad. So one obvious improvement we could make on this algorithm is we can say, well, I don't actually need to search the whole n away from this 1, because as soon as I've had to go more than k indices, then we're back to where we started. No. That's not what I want to say at all. As soon as we go more than k indices, we can go back to where we started and say, I couldn't find anything within the bounds, within the k bounds that it is of the correct value. So that would give us, again, we have to scan n operations, and for each of them we have to potentially move up to k steps. So this is an order nk algorithm. This is almost certainly substantially better. The one quirk is that k can also be very large for this problem. So we could have 10 to the 5 n and 10 to the 5 k. So we're kind of back where we started. Although in practice, if you're doing this kind of problem, there'll usually be some sort of implicit assumption that k is much less than n. So we've gone from n squared to n times k. Can we get this even lower? And I'm going to conjecture yes. Because I have in my head a sketch of an algorithm. So let me try and talk you through what I'm thinking. I don't actually need to scan all of the intermediate values while I'm looking at the 1. If I know where the next 1 is. If I know when I'm looking at a 1 that the next 1 is at index 0, 1, 2, 3, If I'm at index 0 and I'm looking, and the next matching thing is at index 3, I don't need to scan all these intermediate values. So the question becomes, how can I know where the next index is? And I think we can do that by scanning through the list first. So what I want to do is I want to scan this list and basically create a dictionary that says the 1s all live in this location, the 2s all live in this location, these locations, the 3s all live in these locations. And then once I've done that, I can start going through each individual one and say, well, how near are the adjacent ones? So let's say in this one here, I want to build up a dictionary that looks like the 1s live at 0, 2, and 3, and 0 lives at 1. I want to build up this dictionary in some way, because then I can say, well, although these two are too far apart, these two are close enough together. And I never need to worry about this skip distance here, because I'm only interested in the closest pairs. So it's always the adjacent indices inside these lists that I've made. So what's the complexity of that? Well, adding into a dictionary is order 1. So we'll just say that for each, when I'm going through these elements, I want to group the indices by the value. So that's going to take order n time, because I need to look at every element. And then I need to go through every single one of these. Now this could be up to length n, and this could be up to length n. So that, and of course there's going to be n, potentially up to n different digits. So that sounds terrible. That sounds like I'm back at n squared again, because I've got n potential entries with n potential indices. That's n squared. But we actually know more than that, because the entire union of these lists is at most length n, because it's all the indices. So when I'm scanning through these, even if I do them end to end, the most scanning I will actually cumulatively do is order n. So it's an order n pass, and then an order n pass through the indices, giving me order n overall. So this is order n, not n squared, because my two n's are in sequence. They're not nested. So if we're nesting, we multiply. If we're sequencing, we add. So it's order n to scan to build the dictionary, and then order n to scan through the dictionary. Let's actually build this. So locations is an empty dictionary. For num, in fact no, for I num in enumerate nums, if num in locations num dot append I, else locations num equals the singleton I. So what this does is it says, if I've already seen this number before, great, there's already a list there, let's add the current index into that list. Otherwise, there's nothing there. Let's create the list that contains just the index that I'm currently looking at. You could do this with a default dict, but I'm trying to keep this simple. You could probably even do it with something like counter or something. I'm sure there's probably something in the Python standard library to partition indices. So now now I've got all the locations. What I want to do is, for indices in locations.values, so I don't really care what the number is that I'm looking at. I don't care if I'm looking at the 1s or the 0s or the 2s or the 74s or whatever. I just care that I've got their indices. So now I've got their indices, and then what I want to do is, for I in range 1 len indices, in fact no, I'll do it slightly differently. I'll do this to 0 len indices minus 1. Again, this nesting looks bad, but as we talked about before, the total set of indices that I'm going to have to iterate through is only going to be of length n. So this is, although it's nested, the total is order n. So indices I plus 1 minus indices I is less than or equal to k, return true. If at no point did we ever say we've found things that are close enough, then obviously we never found things that are close enough, return false. So this is what might be called eager. So if you have true or something, the idea is that you don't actually care what the something is, and even if that something is very expensive to compute, you don't care. You can just say true immediately. Same thing here. If we get lucky and find the very first thing we check in this nested for loop is two indices that are close enough together that have the same value in the original numbers list, then we can stop there. We're done. We know the answer is true. We have to then try every combination to check that it is false, which is order n. Right, let's run it, do a typo check. Looks good so far. So with our 1, 2, 3, 1, 2, 3, what we would have done, remember, is we've put the 1s together in 0 and 3, 2 is in 1 and 4, and 3 is in 2 and 5. And then we're going to go through, we're going to look at the 0 and 3, say, are they close enough? Nope. We're going to look at the 2 and the 4 and say, are they close enough? Nope. And we're going to look at the 3 and the 1 and the 4 and the 2 and the 5 and say, are they close enough? No. And that gets us, for the last one, hopefully a correct result as well. It does indeed. All right, I'm happy with this. Let's submit it. Excellent. Here, again, we've learned in the past these numbers are fairly meaningless. If I click submit again, I'm just going to get something wildly different. Let's try that actually. Let's show that these numbers are basically random. Yeah, so didn't change the solution at all. We went from 80% down to 20%. So don't trust these. These are garbage. Right. Hopefully that solution made sense. A nice easy one on a Friday afternoon for me. I didn't have to stretch my brain too much, which is quite nice. Hopefully you found this interesting. It's a good beginner problem to think about because the immediately obvious solution is workable. Then there's this small refinement of limiting our search distance to k, and then there's this larger refinement to actually say, well, we don't even need to do this nesting at all. We can do this in order n times. So it's a great problem for actually doing this progression. So that's why I really like this one. Anyway, that's it from me. Hope you have a good weekend. I hope you've had a good week. Do remember to like, comment, subscribe, all of that good stuff, and I will see you next time. Bye.